Okay, so thank you so much for attending the lecture. I know it has been a very long conference, a long school, with 6 days of very intense program. And so today, and you have already seen Jeff's application. And then, so this is another application somewhat different from what he has done. So what I plan to do is, obviously, I will tell you the background of the story I'm trying to tell, and also focus on the complications in terms of modeling, estimation, and how do I get around the difficulties. So what I plan to do is maybe the first part just go through the setting, but focus a little more on actual challenges that you will encounter when you estimate a dynamic model. And then I will present the estimation, and after that, I will then pause for just briefly to summarize all of the different approaches that's, not all, but the popular, commonly used approaches that are out there in the literature. Some of them actually have been reviewed this past few days, and and then touch on, and then continue with the counterfactual. And we have about 80 minutes. I don't think I can cover everything, but I want you to learn how I did it. What are the challenges and how did I overcome them? And without so much emphasis on the counterfactual results. I don't think you really want to remember what happened, but rather how can we use the tools to apply to your setting. So feel free to interrupt me anytime. I think that's better, for the learning process. Okay. Okay, so this application is about industrial policy. I've been interested in industrial policies for a long time. And as I was mentioning this to John, the paper actually has a very difficult publication process. I got rejected in top of the 4 papers before I got lucky in the last journal. Not to discourage you, I still think this is a very important question. It's a very complex setting. So I do have to make a lot of decisions along the way, as you can see. Okay, so industrial policies are widely used in both developing and developed countries. You can see there are many famous examples. Some of us might be familiar with miracles happened in Asia, but in history in the 50s and 60s for Japan and South Korea and Taiwan in the 70s. China, Mexico, India, in the 90s. And then even recently, we actually have seen a resurgence of industrial policies, even in the US and in Europe. And when I started working on this topic, I remember the one common feedback I got is the best industrial policy is no policy. Okay, for a long time, among economists, we all feel that the best industrial policies are no policy. I'm not going to take a stand on whether it's good or bad, but rather we know that this is commonly used. Now let's just analyze it and think about general lessons we can learn, okay? So, as Roderick put it, the real question is not whether we should do it or not, but rather how, okay? So that's what this paper is trying to do. But this is actually a complicated task. The reason is that there are just many different types of industrial policies, and there are many different ways that the government can intervene, can essentially direct the market activities. If you just look at the policy instruments, there are many. You can target, you can have output subsidies, you can have provisions of cheap low interest loans to essentially intervene in investment process. You can have preferential tax policy. We've seen a lot of that. The green energy push, a lot of that is through the tax policies. And then we can influence the trade activities through tariff or non-tariff barriers. And then you can use R&D incentives to incentivize innovation. So we see there's just a vast number of different policies. And if you think about actual implementation, which is what this paper is about, there are even more questions to be answered. When should you target? Who should you target? How should you target? Should it be uniform? Should it be discriminatory? There's just a lot of different questions, okay? And I don't claim to answer all of them, but I try to essentially first put them in a framework that I can analyze them and try to think about general lessons that perhaps we can gather. Okay, so what did we do is focusing on a particular example. where we look at the global shipbuilding industry, where China intervened very actively from 2005 onward, actually from 2004, for about 10 years. So we collected data spanning from 1998 to 2014, and to look at both what happens before, what was going on before, and what was happening after. Okay, and so for those of you who might be who might be familiar with China's industrial policies, often the major ones will be the 5-year plans. And indeed, the shipbuilding was dubbed as a pillar industry in the 11th 5-year plan and 12th 5-year plan. So that was the focus, where we'll first use the policy documents to essentially identify the areas where the policies hit the firm activities, and trying to estimate, quantify how big the subsidies are, because we don't really have data on the exact amount of subsidies that government provided, and then do the counterfactual. So that's where we're going, okay? Yeah.
Was the motivation for this industrial policy to avoid dependence on foreign shipping, or China's expanding its exports, so it wants its own ships to make sure that they're more reliable?
That's an excellent question. In the data, we never know what the government objectives are. We try to read a lot of the government documents, but that's not something that the government explicitly say, okay? At the end, we're going to do all of the traditional rationales for industrial policies and try to see, well, those actually are not supported by data, and here are a few that potentially could be the reason. So at the end, indeed, I'm going to go after this question: what was the initial purpose of those policies, and what can we learn from that? Yeah. And the challenge, I've any? Okay, and then so initially, the first few years, actually the industry was booming, was expanding very fast, as I show you in the data. But then quickly, it was hit by the financial crisis in the middle of the expansion period in 2008, 2009. Then the ship prices plummeted, and then the government changed the policy, put in entry ban, and then shifted the subsidies toward large and existing firms, and then finally had the consolidation list. Okay. So in the analysis, I need to address a challenge that has this pronounced business cycle, boom and contraction, and I have to essentially identify the key targeting point of the policies, and that's what I'm going to do, okay? So this paper is much of the existing empirical literature focus on the rationales. We want to have industrial policies because it corrects externalities in most of the cases. But almost no paper have looked at the actual implementation, as I mentioned, right? When should you target? Who should you target? How should you target? And which part of the production stage should you target? And so that's what we're trying to do. It turned out we can actually learn a lot about the policies by looking at this more carefully. And that's also because, as an economist, I can't tell you the general equilibrium consequences. I can't use data to say what's the spillover from shipbuilding to the entire economy. I think those kind of empirical exercise is very dicey and difficult. Okay, so I'm just going to focus on one sector and think about how can we learn. So that's the approach I'm going. But I do need to incorporate those prominent features in my analysis. So I have to have a real business cycle. How do I capture that? I also have to capture the fact that there are multiple policy instruments. I'm going to show you how I do that. Finally, there is, even in this industry where you have a large number of players, firms are different. Products are different. Heterogeneity is important. So I think I'm sitting at the center, at boundary of macro and micro economics. I need to have a reasonable business cycle, but I also need to have reasonable firm heterogeneity. This is particularly important when I look at firm investment decision, which is really the fundamental decisions that industry are making, that the firms in the industry are making to change, really shift this, the process of the industry. So I have to have both. Okay, that's where the difficulties come in. And so, as a standard dynamic paper that you have seen in the past few days, firms are going to have both static and dynamic decisions. Here, they're going to decide on production, and then importantly, they're going to decide on investment. That really characterizes the rise and expansion of the entire industry. And that's a focus of today's analysis. But then there will be enormous amount of entry and exit, especially in the booming and contraction period. So I need to have both. For all four of them, entry, exit investment decisions are dynamic, right? We know this has dynamic implications. Production could be dynamic. This is actually Myrto's job market paper where she showed, the dynamic, there's some dynamic elements in the production. Here, we're just going to assume production is static. The reason is, as you can see, the industry expansion is primarily driven by the investment process, not so much about the timing of the production, okay? And our results actually are similar to hers, even though we don't, in terms of the subsidies we recovered, even though we don't focus on production dynamics. There's only one paper, by the way, I've seen that has a dynamics nested within a dynamics, have a dynamic production nested within a dynamic investment. And then that's a paper done by Mar and her co-authors, which is currently R&R at AER, in a setting of electricity expansion. I've never seen any other paper that has dynamics nested within a dynamic problem, okay? That's just too hard, okay? Okay. So we ask the following questions. First is just to do an evaluation. Okay, what has happened? How have the policies affected the global industry? And more importantly, we actually want to understand better what are the relative performance of the different instruments, production subsidy, entry subsidy, investment subsidy, etc., or the consolidation policies, which ones work better. I don't think I want to focus much on that. If you're not interested in industrial policy, probably don't care. And finally, toward optimal policy design. And then at the end, we talk about rationales, okay? So I want, maybe the focus of today is really how I did the exercise rather than the findings that I have. Okay, and then so I won't go through the papers just in the interest of time, okay? So I will first talk a little bit about the industry and then the challenges in both the institutional details and data that I need to confront, and then the model and then estimation. Okay, so first of all, I have to decide, what are the important product attributes? What are the important market features? So here, when we look at the ships produced by all different countries, there are actually many different types of ships. And we ultimately decided to focus on three: the bulk, the containers, and the tankers. The reason is the other categories are very specialized, and the production worldwide is very small. Most of the times, just a few ships per year. And so those three categories account for the 90% of world production. So naturally, I'm just going to focus on the most important categories, okay? And then within each category, the bulk, tanker, and containers, again, there's the question of how fine do you want to go? Okay, even within bulk, there are different sizes of bulk ships. Containers, same too. The question then, it becomes quite clear later on as I show you the different state variables. It's very hard to go further than that. If I have 10 different products, then I have 10 different prices. Just the price variable, I have to keep track of 10 state variables. And fortunately, in our setting, this industry has come up with a measure called compensated gross tons to precisely address this problem. The ships are heterogeneous, size difference are huge, even within the category. How do we evaluate, how much is the worth of a ship? So the industry has this well-accepted measure called compensated gross tons so that you can compare ships. Essentially, it boils down to price per ton, price per size of the ship. And so using that metric, we can actually, all the ships are within the bulk category look similar once you can control for the size of the ship, okay? And then if you look at the price variations within this bulk, once we control for the size and market dummies, meaning the year and quarter dummies, the R squared is 0.9. So essentially, I think we feel comfortable that this is the right level of market definition. Those two different types, actually they ship different products. That's why they're somewhat, segmented. Okay, so the bulk ships, bulk ships carry raw materials, tankers, they carry oil and chemical products, and then containers, they carry essentially containers, okay, container ships. Okay, So those, as you can see, those ships are gigantic. Many of them will be hundreds of millions of dollars. And then so they are also heavily influenced by industrial policies, which is why this is a good example. And if you look at, this is 100 years of market share, okay, based on the orders. And for much of 1900s, last century, I feel odd talking about it as last century, that Britain was very dominant, and partly because UK actually has had supported the industry pretty aggressively. And then followed by the US only appeared in the two world wars, where US massively expanded production in order to essentially for military purposes. And then Europe and Scandinavian, they are dominant because of the trade. They were the dominant maritime trading countries, and so they also dominate production of ships. Then coming into the 1950s, you see the rise of Japan. Japan targeted shipbuilding as part of their industrial policy to rebuild the country's industrial base. And then South Korea and then Japan also has had very long tradition in maritime trade. Then in the 70s entered South Korea, which is actually quite different because South Korea did not, unlike Japan, have a very large trading economy. But South Korea identified shipbuilding, just to essentially copying Japan in the 70s and 80s. And then China, as you can see, started in 2000s, okay? So that's essentially, this is an industry that has been heavily intervened by different countries. And that's why we go, at the end, we're going to go back to see what are the rationales, why do countries do this? So then the first thing, I have finally had a market, and then I obviously need to identify the policy. So here we went through all the different policy documents and identified the three buckets of policy that target production, investment, and entry at different points in time. So I just take that as given. Those are announced policies, and I'm just going to take the time of those, the blue ones, the 06 and 09, and 13 is at the end. We do that for counterfactual to say, okay, here is the policy intervention. So here's actually a stance I'm taking. I will show you in the modeling, which is I assume the policies are not anticipated, and then once they're in, firms assume they're permanent, okay? It's not perfect, because firms probably don't think the policies are permanent, but 5 years or 10 years are long enough, with a discount rate of 94 or 95, those are long enough. So I assume they are permanent. When we did, in order to think about this, we actually shifted the discount rate in order to essentially to mimic in a reduced form firms prior about how long the policy will last. The qualitative results are similar, okay? But that is an assumption. Okay, so let me show you some data patterns. As you can see here, China, 2004 is when two provinces, the most important provinces, producing provinces in China, started targeting shipbuilding. But then 2006 is when the country started, 2005 and 6. You can see this massive expansion during the 2009. So quickly, China took over. Before the policy, the market share for China was about 10%. Once the policy hit in just a few years, China's market share was, exceeded 40%, and eventually become the leading country in terms of total tonnage. And today, China is still competing with South Korea head-to-head, in this market. And then this is another reason that dynamic models are crucial in analyzing these kind of problems, because the intervention, has long-term implications. You can't really use a static framework to analyze, how has Chinese policy affected, the global industry, etc. So this is really a setting where dynamic models are important. Okay, and then you can see, this is what I meant, the boom and bust, as you can see, in 2006. So usually, in South Korea and Japan, there's very limited entry, maybe 1 or 2 shipyards per year, so I'm not going to model that. But before the sample, China's entry is about 10 to 15 shipyards per year. And as you can see, at the peak, there will be 50 new shipyards per year. Okay, so the massive entry. And then once the entry ban was hit, then only those pre-approved firms can enter, or the shipyards that change their production can enter. But so this is a very pronounced boom and bust pattern. And then this is the investment pattern that I think best illustrates that the scope and the importance of industrial policy. There's no other economic arguments that can explain this threefold increase in just 1 year. And so, naturally, you think that maybe firms would expand, invest for some other reasons. They're efficient, they're entering into new market. But if you look at this sector, everybody was expanding, regardless of size, regardless of their region, regardless of their home ownership structure. So this is, to us, the most obvious and convincing evidence that something else, in addition to economic factors, are influencing firms' behavior. We're essentially using before and after to refer what must be the amount of subsidies the government provided to rationalize this kind of threefold increase in investment. Another pattern I want you to mention, as you can see, the investment was elevated post the financial crisis when the ship price was so low that most other countries are shrinking. And that's another evidence, again, in 2009 when the government then shifted the policy support. And this, again, will be evidence that non-economic factors are influencing firms' investment decision, post the financial crisis. Okay, so now let's talk about the model. In 2011, the ship prices were so low, you didn't really want to invest, even in 2011. So we actually estimated that this part here is, again, explained by actually higher government support. Otherwise, there's no reason you should invest.
Even if it went down?
Yeah, just because there's so much excess capacity, you don't really want to build your capacity when you can't even have an order.
So other countries did not go up their investment?
There's no investment anywhere else. Yeah. Okay. So now let's actually think about the different elements, right? I just mentioned how I characterize the market, the product, and then so we have firms. So we have Chinese firms. So the industry is essentially controlled by 3 countries in this period. So I'm just going to focus on firms in Japan, South Korea, and China. The other countries account for a very small fraction, less than 5 to 8% of the total production. And then so the decision is mostly dictated by data because we don't see any expansion entry-exit from Japan, South Korean firms. So we just assume that they're not really actively expanding. Actually, after 2014, South Korea counteracted. So if I were to write this, have the data until today, then I will need to build in the dynamic decisions by South Korea, okay? So for this sample period, then the firms are, of the dynamic decisions, entry-exit capital accumulation are done by Chinese firms. It's just dictated by data. It's not because we don't want to model them. And then so we have different ship types, 3 types. Then we need to add, because they are essentially sub-markets, we actually need to follow the prices, capacity, in those 3 sub-segments. So the assumption is that ships within a type is homogeneous up to their size, which we model. Okay, so then there, again, the government subsidies, as I mentioned, we group them into 3 buckets, okay? Then the exercise is to recover the magnitude of the government policy intervention along the 3 dimensions. So I need to estimate how much the government is subsidizing production, how much they're subsidizing entry, and how much they're subsidizing investment. Then in a counterfactual, I can either turn on and off different policies or maybe have different magnitude in order to try to get a sense of how can you do better. And then so then those are, the government subsidies are essentially modeled as a shift, okay? As a shift in the cost of firms perceived as permanent by firms. So that's an assumption. Okay, I can use a discount rate to do a robustness on that. And then the 2 policy shocks, one in 2006, the other one in 2009, where both the amount has changed. As you can see, there's consolidation after the financial crisis. Then the consolidation policy is 2013. That's already at the end of the summer period, so we're not focusing on that. We just do the counterfactual for that. And then they are perceived as unexpected and permanent, okay? And then then I need to figure out the payoff relevant variables, which I will show you. And then I also need to have the transition process. So what I'm assuming is because there are actually government interventions, that they are still Markovian pre and post policy intervention. So that's the assumption. Otherwise, if I don't want to get into a non-stationary dynamic model, just way too hard, okay? So right now, assume a stationary conditioning on the policy, okay? Okay, so then think of the timing. The time is discrete with an infinite horizon, and then there are J farms. So the incumbents, they draw productivity. I have to model their production decisions, and production, as you can see, there are actually some tricks I need to, some hurdles I need to overcome. And then they choose productivity is realized, and they choose quantity, and then they receive payoffs. Farms are different in their cost of production. So that's first a primitive I have to recover. That's how some farms produce a lot and receive a lot of orders, and other farms don't. Okay. And second, the existing farms then have a random scrap value, and then decide whether to exit. And then continuing farms decide they also have an investment cost. This is actually what I focus on in this discussion today. And then they decide how much to invest. And the entrant then draw entry costs, decide whether to enter. Then at the end of the period, all the decisions are realized. Then we start a new period. And then, so what are the relevant state variables? I've already mentioned, at least in a minimum, this is a kernel model, right? So prices are important to determine firms' profit today and tomorrow. So I have to follow the three prices for the three important markets. Some firms sell to multiple markets. And then in terms of the firm, naturally, the capacity matters. That dictates their marginal cost of production. And everything, many other features that also characterize why some firms are good, some firms are bad, are natural payoff shifters, right? Payoff relevant variables. And so indeed, country and region matters. South Korean firms, are more efficient. And then the ownership status matters. The SOEs are large usually, and then they're efficient in different ways. The backlog, which is just a reduced form way to capture the dynamics that Myrtle emphasized in her paper, which is the amount of ships orders you're working on at the same time can make you, if you have a larger number of orders, you might be more efficient. Okay, so that's another state variable. And finally, capital is very important. So you can see immediately I have a very large number of state variables, and many of them are continuous. So then I face the question of, do I want to do the discretization full solution method? Then if I really went through the discretization, maximum number of values per state variable would be 10. But 10 is too discrete. I essentially have to lump farms. Actually, even 10 is too much. 10 to the power 8 is too big. But I have to lump farms into a very rough bucket. Okay. So instead of discretizing the state space, recognizing that firms make very different investments and firm size are different, actually the prices are very different, I decided to go through the continuous approach, and which means that I can't really use a standard full solution method and have to find something else. And eventually I decided to use, John. Ships live. Yeah, that's very important in demand. And indeed, that's one of the key shifters in aggregate demand. Ships live about 20 to 30 years, and then the fleet at different size is a very important shifter in aggregate demand for new ships that we capture. And that's all in demand, and that actually is very important in the counterfactual. But here, the dynamic problem is focusing on recovering firms' cost of production, firms' cost of investment, and firms' cost of entry and exit. And yeah, so I will. That's part of the analysis, but more important for counterfactual than for the estimation per se. Why back out?
If you have the infinitely powerful computer, you want to model the secondary market for ships too, right? And then there's the demand, and when firms start scrapping those ships, the demand, and then there's
That's exactly right. And here, as you can see, essentially the assumption I'm making is the ship prices are sufficient statistics as predictor of my tomorrow's profit. So all of the second-hand used ships are going to influence the ship prices, but I'm essentially using a reduced form approach to capture how the ship prices change. That's exactly right. And in a counterfactual, that's actually the hardest part. How do I capture in a different world, how will ship prices respond? Okay, so now let's start with the simple ones, okay? So you see there are 4 different decisions. Production has no dynamic implications, so let's start with, first let's model demand, and then let's model production, and then I will model investment, entry, and exit, okay? So demand here, as John pointed out, the aggregate demand for for container ships depends on, the freight rates, how much the shipping company can charge, and depend on, so for bulks, the commodity prices, that essentially dictates how much commodity trade there will be, and how much demand for the shipping services, and how much demand for new ships. And so I have to control for that. And then total fleet. If there are already a large number of existing ships, I probably don't want to order new ships, okay? All of that are relevant for counterfactual as I predict new ships prices, but not for the dynamic analysis when I'm trying to back out firm's production cost or investment cost. Okay, so that's the first step. And then the second step is I want to essentially be able to predict the production decision that determines their period payoff, period profit. And so here I'm using Chrono model, partly because the ship prices, once you control for size and time, doesn't really vary much. So their profit is price of the ship for the ship type times quantity they deliver minus the cost of producing this much of different size of ships. And then this will be, once I have the cost specification, then the model will give me naturally marginal cost equal to marginal revenue. It will give me Q star, how much you should produce. It's purely dependent on the ship price and your efficiency, how efficient you are, okay? And then the supply and demand will essentially determine the equilibrium ship prices. In the estimation, I see the ship prices. I don't need to predict. This is only the object of relevant for counterfactual. When I shift counterfactual, firm's quantity will change, okay? Because firm's production will change, firm's supply will change. Then I need to intersect this counterfactual supply curve with the demand curve to get the counterfactual prices in a but-for world, in different settings. Okay, sorry. And then the second is the dynamic decisions, okay? So the investment, as I will focus on, I will tell you how I do the investment. And then provided that you have the investment, then the capital transition process is deterministic. We just have a deterministic depreciation and plus the new investment. And then so the Bellman equation for the firm is, for existing firm, you first have your profit from production. Then you decide whether to exit to get the scrap value, or you choose your investment. You have to pay investment cost to begin with, and then you collect future value, right? Why does investment affect your future payoff? Huh? Exactly. So because here, so here, investment will increase your capacity, which will then affect your cost of production. So that's a very important state variable that affects my future production costs, which hence increase my future payoff. Okay, so this is the part, as you can see, that I have to figure out. In this model, I have to solve the optimal investment first. But solving the optimal investment requires me to know what the future value is. That's always the conundrum. That's the difficult part of the dynamic problem. So I will come back to this. And then the goal is to estimate the cost of investment. So previously we estimated investment the cost of production. Now I need to estimate the cost of investment. I also need to estimate, what's the rough size of scrap value, right? That's recovered from the exit decision. And then I also need to estimate the size of the entry cost. That's essentially recovered from entry decisions that I observe over time. And then And then so this model here conceptually will deliver, once I know all the parameters, it should deliver predictions of production, entry, exit, investment that I can take to data. Okay, so now I will first show you some data patterns, and then we actually think about how to do that. So the data is, we have, so ships are, because they're so large, almost all of them are intermediated by brokers. So that's why we have very good data. So essentially from Clarkson, largest intermediary in the world, we have all of the quarterly data on prices and quantities for all the firms participating. So that's really, a very nice P&Q data. And then we augment it with the Chinese data on Chinese firms to get our investment and firm attributes. Okay, that's what we take to the data. And then we identify the government policy. Okay, so here are some of the, essentially we have about 10,000 data points on orders and then the firm's backlog, essentially how many ships they're working on, the capital size, investment, etc. If you look at this, you recognize actually a large number of quarter firms don't have any positive orders. And this is very pronounced in business cycles. For industries with very large business cycle, the capacity utilization rate changes a lot. And in our particular case, there are a fair number of firms with zero production. So this is actually a challenge that I have to overcome. And then so I will show you later how I do that. And second, as I mentioned many times already, there's a very pronounced business cycle, right? So ship prices, as you can see, has this shape, very pronounced U shape, inverse U shape. What would be a good way to model this? This is a transition. Here I need to essentially forecast tomorrow what's my profitability. And the key element in a dynamic model estimation is a transition process. I need to predict from today's ship prices what tomorrow would be. What would be a good, reasonable transition process that can capture this boom and bust? Should we do AR1? Huh? What would AR1 process give you? Yeah, it will essentially look like that, right? It will plateau at some point. Clearly, this will not work well with just a very simple AR1. We tried a lot of different things. We don't really have good solutions. We literally just have AR1 with a trend break. Okay, nobody foresee the financial crisis coming. So before financial crisis, they are working with an AR1. After financial crisis, they work with a different AR1. So we just had an AR1 with a trend break. Okay. Now let's look at the estimation. And so think about the state variables. I have a fairly large number of individual specific state variables, and then so for every ship, every shipyard, every farm, they have 3 different type of products, and the backlog size, they have 3 backlog variables, right? That's 3, and then capital 4, and a bunch of size and region and the attributes that don't change much. Then I have the 3 ship prices, aggregate state variables, 7, and then I have industry policies, and this is for counterfactual. So in the minimum, in the most sparse specification, I need to handle 7 continuous variables and a bunch of the transition in the fixed, not fixed, discrete state variables. So that's why discretization full solution method is very, very challenging. And then so let's start with a simple one. Let's think about the dynamic decision production, and then we'll spend quite some time. How much time do I have?
1 hour and 20 minutes, and updated programs would go until 12:05.
12. Okay, let's do 12. We'll have 35 minutes. Okay, so I spend about 20 minutes on the estimation, the dynamic part, and then we're done. If you're interested, you can read about counterfactuals. And I will answer John's question at the very end. Why are they doing it? Okay, for production, this is the marginal cost specification, which is pretty standard. You have shifters affect whether you are, efficient or not. And then we also care about convexity of, production. This is so most of the demand analysis, when we do first of the condition, we assume there's a way firms have constant marginal cost. But in reality, for the, firms that are, in heavy manufacturing industries, convexity is very prevalent. because you see firms expand their production when prices are high. If there's no convexity, you won't see that, okay? And then so this is a key, and this is also one factor that why affected the return of the industrial policies. If firms are already producing a capacity and you want hit with additional subsidies, it's going to lead to very, very costly production. And that's a key message that we learned. Very simple intuition. Just because they're already producing at the level of high marginal cost, producing even more will simply increase the cost of production, okay? And then so that, as you can see, we have a large number of firm-specific or aggregate, shifters that influence their marginal cost of production. And then, so the capital is a key that we want to focus. This is really the link that makes this a dynamic model. If capital doesn't really influence your production of marginal cost, there's no dynamics in it, okay? And then the backlog is another way to essentially capture this economy of scale. We're not really modeling the capacity in a very serious way. We just use backlog as a proxy. And then firms have productivity shock, and then firms compete in chrono. So we're not having dynamics here, but our estimated cost subsidy level actually is similar, to Mirto's estimates when she has dynamics. And here, firms equate marginal cost with marginal revenue. So let's take a look at this shock, okay? Most of the time in many other studies, the productivity shock is just a nuisance. It's a residual that you try to fit that why firms produce a little more, a little less. Here, it plays a very important role. Why? Because if my shock is very negative, I'm not going to produce. This is actually a case where I see visibly that there will be zero production. And so the cost is an important way for me to rationalize why in some of the peers you actually don't produce at all. You're just hitting by a shock. And second, as you can see here, a lot of in some periods, okay, firms don't have zero production. Another reason is simply because there's a fixed cost of production. You have to have if you want to produce, you have to essentially have the entire crew in a dock and heat up have the big crane in order to deliver, essentially put things together. And so another important aspect is that the fixed cost is relevant. In most empirical analysis, fixed cost of production is almost always ignored. The reason is you never see firms produce or not produce. And the produce or not produce margin can only, essentially, that's the data variation you need in order to identify fixed cost. And for us, that's a very important aspect. That also explains why, certain policies, if the firms are essentially, if the policy is hitting the marginal firms in choosing between producing and not producing, most of the subsidies are wasted on this element here. They're not very generating efficient or useful production, okay? So we're going to essentially estimate the fixed cost production and then paying close attention that there's no production, using those two, or that's a lumpy. Okay, so then if we impose some distribution assumption here, we can have a serial correlation. Then we can essentially model the likelihood with what's the probability that you produce positive amount, so that marginal cost equal to marginal revenue, and what's the likelihood you actually don't produce, okay? So that's the marginal cost. That's relatively straightforward and easy. Okay. Now let's think about, and then so some of the estimates. Okay, so here you can see all of them are state variables, meaning in my dynamic analysis, I actually have to track all of them. You can see how many I have, right? A large number of state variables. So there are several tricks. Here, you can see the size, essentially the region dummy, ownership dummies, all of them do not change throughout my sample period. So they enter into my marginal cost as X beta. And rather than tracking each one as a state variable, I just track the sum as an index, one state variable. So that's a very important dimension reduction. So all of them here, except for this, essentially just one state variable, okay? And then I have one index and one subsidy. That's another state variable. And then I have a bunch of continuous state variables that I need to keep track of. Okay, so there are tons of summaries. So indeed, convexity is very important, and that's going to influence the policy efficiency. And then there's also the, capital is also very relevant. If you double your capacity, you push down your marginal cost by, by here, 38%. And that's why large farms are much more efficient than small farms. And then so if your policy induces entry of very small farms, it's clearly not very efficient. Yeah. That's a very important question. Here, I'm just using capital size to proxy for dock size. So I'm not really estimating, focusing on the capacity constraint issue. Partly because I think capital does a good job, and partly because much of the issue is actually underutilization of capacity rather than capacity constraint. Yeah. Okay. And then so this part here essentially characterizes the dynamic implications of investment. This is influencing the efficiency for the public policies. And then here we also find some kinds of economy scale and capacity constraints. We're just using reduced form that if your backlog is too big, you're hitting a capacity constraint. If it's smaller, then you actually have economy of scale. Okay, let's now look at, then we have, so here, the production subsidy essentially recovered from differences before and after, and differences between Japan, South Korean farms versus Chinese farms. Okay, so that's really what allows us to identify the subsidy size. And then, so here are, those are, we did a lot of robustness analysis. I don't want to bore you with that. It took us many years, but it's not very important for today, okay? So now let's, the model fit is good. Okay, so focusing on the dynamic element, and especially focusing on investment, let's think about what are the challenges I need to overcome. So here's a dynamic model, right? Very simple. Your value function depends on the state variables. Remember, I have a large number of them. And also your scrap value. This is an ex-ante value function for incumbent. And so production I've already analyzed. The production is already optimized. So I know the form of the profit. So pi is a function of all my state variables that I've already solved. I just estimated that in a previous step. So I know how pi depends on S. Okay, that's given. So now I'm just going to decide, do I want to exit to get the scrap value, or I want to continue, in which case I get a continuation value, which as you can see depends on my cost of investment today and tomorrow's benefit from a larger farm. Okay? So there's this shock term here, nu, as you can see here, that my specification of the cost of investment first depends simply on the unit cost. If I spend $1,000, the cost is $1,000. The second term here is random cost. We're using that to capture the fact that observational identical farms make very different investment decisions. Even if they have the same size, same ownership, same region, they often make very different investment decisions. You can think of the reasons. Maybe they have different connections to the capital market. Maybe sometimes they get preferential size. There are just many different reasons why farms make different investment. So that's what we are capturing, that the cost of investment is random. So the marginal cost of investment is nu, plus a bunch of other stuff. Okay? And then we all know that farms don't make infinite investment. The reason is that investment is costly. So there's a quadratic adjustment cost as you increase the investment size. And finally, T is a policy. So in the 2006, when the government subsidizes, then the cost of investment goes down. Okay, so C4 is for each dollar of investment, how much is subsidized by the government. We have done a lot of, so this is actually we borrow from the macro literature. We checked for different other specifications of adjustment costs, random fixed costs, irreversibility. Once we have this term here, the others aren't very important. The macro papers do not have this term here. they're not really focusing on heterogeneity across firms. They're not really interested in understanding why some firms invest more and other firms invest less. So mostly it's just an aggregate investment that they're after. But for me, I actually care about the heterogeneity. This is a key finding that firms are not equivalent. In fact, they're very different in terms of their efficiency. And if you target efficient firms, the outcome of the policy could be much better. So we actually care about the firm heterogeneity. And then so once you have this term here, okay, what's the implication of this cost specification? Then investment would depend on which variables once I have this specification. What would the investment depend on? It would depend on the state variables that I have capturized. It would depend on the policy. If the policy is very generous, maybe I invest more. And it would depend on the new. This actually induces a very important selection because firms don't just make random investment. Rather, they invest when the time is opportune, when it's a good time to invest. If you ignore this, you're going to, so there's a negative correlation here. When my cost is low, I'm going to invest more. If you ignore that, you're actually vastly underestimate the cost of investment. So then, counterfactual, firm just invest way more than reasonable. So this is it's like the selection in price. Consumers don't just randomly, the price is endogenous for a different reason. Here, the investment I depends on all of my state variables and this unobserved investment shock. Okay? And if I don't correct for that, then I essentially vastly underestimate the real cost of investment. Okay. So then I have, here's my value function, right? So what are the challenges? And here I have to essentially figure out a way to formulate the optimum investment that depends on both the state variables, the policy, which includes the policy intervention, and this unobserved shock. So okay, I already told you the answer. So that's the challenge, okay? So investment is an incredibly complicated object. If I knew the value function, the function form of this, then I can do marginal cost equal to marginal revenue. Even that is not trivial. It involves the integration, derivative of the value function. And then if I want to calculate this, right, here, because I want to integrate out this shock, I have to simulate all of the investment shocks and then plug in this optimal investment policy and integrate out the whole thing. You see? Yes.
Okay, so there's sometimes I0.
Yes, exactly. Sometimes I don't want to invest. Exactly. If the new is too big, too big, you don't want to invest.
I see. So it's not like there's a sunk cost of investment. It's just the new shock that rationalizes the negative to zero.
It rationalizes both the fact that many periods you don't invest and the fact that many firms, even if they look identical, they actually make very different investment decisions. Yeah. Okay, so how should we do? It looks like, I don't know how to do the value function yet, right? I haven't told you how to do that. And even if I do that, okay, that's the solution. And then I have to figure out how to characterize the optimal investment. So this is actually a difficult problem. We thought a lot about it. How can we characterize the optimal investment without solving the value function first? This is really key. If I solve that, then I can just use the BBL forward simulation, right? I know my policy function that's in data. I can simply forward simulate and calculate the discounted sum of future profit, like Ari explained yesterday morning. Then I'm done. That's my proxy for value function. How can I characterize the optimal investment without solving for the value function first? John?
Why not do like Google and you do reinforcement learning with DQ methods?
That's not, okay, that's a good, that's not the right solution because there's endogeneity in it. Remember, I argued firms don't really invest randomly. There's this unobserved random shock that they make opportune investment when time is right. If I ignore this completely, my estimate of investment cost is too low. Okay, so that's the hard part, okay? The solution is, let's think about some assumptions. Actually, this is a paragraph in BBL. Nobody, the author already thought about it, but I think we're the first implication. There's a monotonicity assumption that we can perhaps feel comfortable to impose. What we're going to assume is conditioning on the state variables, which we already have a large number of them. Then if you make a larger investment if the cost shock is more favorable. Okay, conditioning on state value, then the future value is already determined. Then the only thing is your marginal cost. If my marginal cost is very high, I'm going to invest less. If my marginal cost is low, I'm going to invest more. That is a very powerful result, monotonicity. So as you can see, if you are willing to assume this assumption that investment conditioning on S is monotonic in nu, okay, then I know nu. Why? I can look at conditioning on S. I can look at my empirical distribution investment. If you are investing at the 90 percentile of the distribution, it must be the nu is at the 90 percentile of the whatever distribution you're assuming. So this is incredibly powerful. Okay? So this is actually have been used in a lot of settings, control function approach, even in demand. We don't know delta, but we're essentially inverting delta based on the market shares, and that's exactly the same here. So once we have this assumption, as you can see, then the jth quantile of my shock corresponds to jth quantile of my investment, vice versa. The jth quantile of my investment tells me what the value of nu ought to be. And specifically, I can now characterize the relationship my I star as a function of my nu, condition my S. It's literally just what I said here, okay? So this, as you can see, this distribution corresponds to this distribution. So the I is simply an F inverse of the nu's distribution. Empirically, because I need to simulate, right? I draw a nu, and if the nu is at the 10th percentile, I just look in the data, what's the 10th percentile of investment in my data, and boom, I'm done. I've solved this complex object. And then, so next step, as you can see, so now I've essentially used the data to invert this complex object of how investment depends on both observed and unobserved state variable, right? Now I have a policy function. The next step, as you can see, is the fact that the value function is still unknown and potentially difficult. Any question? Yeah. Yeah, so G, any distribution here, it will work, because all I know is monotonicity. I don't really know the location of G or the scale of G. And as you can see here, if G is very unfavorable, if your cost shock is so large, your marginal cost of investment is large enough that exceeds the marginal revenue, you're not going to invest. So this nu itself will essentially rationalize zero investment as well as different size of investment. Okay.
But you still need to. I think she was asking about truncation. So you still need to.
Yeah, exactly. For some of the distribution of nu, I'm not going to invest. You will have, for maybe when nu is below 50 percentile, you see no investment.
You know the distribution of G in the tail. What you need is sufficient.
So it's okay for 50% of for 50% of the nu's, the I is 0. Yeah, that I can just read from data. That's.
You're going to use parametric model for G to get to the tail to extrapolate it.
No, as I said, I'm literally looking at data that I recognize that, maybe I have 0, and then I have, for 10% of the time, firms are not, actually 50% of the time, firms are not investing. It must be that 50% of the news, I'm not investing. My optimal I star is 0. Okay. Yes, otherwise it's a non-starter. I might be able to, I don't know, I might be able to have some correlation just because of monotonicity assumption, but I will leave to the econometricians to figure out how to deal with, the unobserved state variables that are correlated with the observed state variables. That's a very hard problem. Okay. So the second step, I will speed up, is the value function, right? I've been dancing around this topic. Now let's face it. The value function is very hard, as I argue. I can't use discretization because that just leaves with me a very rough step functions with very limited number of state values per state variable. So then I thought about maybe we could do approximation. Okay, the reason is that in many cases the payoff function, if you look at it, it's actually very smooth. For Cournot is the case. For differentiate demand, Bertrand-Nash, the payoff function is still very smooth. There's no junks, weird. So essentially, and then if you think about the value function, it's a discounted sum of your future profit. If the profit function is smooth, then the value function, obviously there's exit probability, etc., will also likely to be smooth. That's what, I think motivated me to go follow this approach. So let's assume that this is a discount sum of future profit, so I can probably approximate well with some kind of basis functions. Okay, here 10 years ago I was using the splines. Today I will show you how to be fancier and do a better job. But ultimately it's just some basis functions, and you can think, for simplicity, just think of this polynomial. We all know what polynomial looks like. And then so I can see I've transformed an unknown function into a known function that I choose, polynomial of order 2, for example, with unknown parameters gamma. And so my value function, this is my Bellman equation, right? So now, as you can see, pi I've already characterized. This is just the parameter of my distribution of my, this is exit probability times the mean of the exponential distribution. That's one parameter. And here, which is continuation value, is a bunch of parameters that characterize my cost of investment. Remember, I've already figured out how to do I star. And this part here is just a bunch of basis functions and unknown parameters gamma, where I'm integrating out tomorrow's state. Okay, so I essentially this is a function of tomorrow's state. And I've already, this E function is how the state variables transition. Remember that I've already used AR1 with a breaking point to characterize the transition process from ST to ST plus 1. And this part here is just a function of finite number of unknown parameters gamma. Okay? So up to the parameters I've now constructed my value function. Yeah.
And so I guess, can you say anything about?
Excellent point. Excellent point. So now, exactly. Exactly. Now let's think about this problem, okay? A very large number of state variables. How can I come up with a good basis function? If I just have 10,000 data points, not a very large data point for estimating, as you can see, basis functions with a large number of state variables. It looks like I need a million. Maybe even a million observations is not enough. So what should I do? I'm looking for some inspiration in the room. The trick is, which is again what I'm going to show you later, is remember, this is essentially I'm looking for the basis functions that can rationalize or approximate the shape of the payoff function well. But the payoff function is known. Didn't I tell you that I know the function formula is pi of s? I can evaluate the pi of s at infinite points up to the capacity of my computer. I can generate many different, different data, sample data, pseudo data that I can use to train my basis function. And that's exactly what I'm going to talk about later, for some new methods. Okay, so that solves the problem that, even though my data is limited, I can actually construct a large number of data points to find what basis function works best. And so as you can see, now the Bellman equation is just a bunch of known functions and unknown parameters.
Sorry, how does that, this bunch of interaction between all the state variables, how is that captured?
Yeah, I know this, the profit function is a function of price, quantity, and all that, marginal cost. With the parameters all estimated, I can construct what the firm's profit would have been under any hypothetical S value. I've already estimated the cost of production. I know the price. Give me any hypothetical ship prices. I can tell you what the firm's profit must be.
Well, it also includes cost, right?
But I've estimated the production cost, the dynamic cost, which is here, as well as the exiting cost. Those are things I need to estimate. I will show you how I estimate the dynamic cost. But to construct the basis function for value function approximation, I have infinite number of potential observations I can use. Okay? Okay.
Just to follow up, so just make sure I understand. So S has many dimensions.
Yeah.
You cannot do polynomials in more than 4 dimensions.
But, okay.
So what I think you're doing is that you're saying I'm going to replace S by pi j, and then write a polynomial in pi j.
No, I'm not doing that. So S is, maybe make the case of 2 continuous variables. I can generate infinite values of those 2 continuous variables, which means I can generate a very, very long vector of the profit equation, profit here, a very long vector of the profit that I can use to fit or train my basis function.
But I guess my question is, you have many firms in the
Yeah, true.
So the state, if each of these firms have 2 state variables,
Okay,
then S is 2 times,
No, I do not have. Okay, the capital is one state variable that characterizes different firms' capital, where the capital is, right? It's one state variable. It's not one state variable per firm.
Why is it not one state variable per firm?
Oh, because the impact on my profit is the same regardless it's firm I or firm J, as long as the capital size is identical.
But the incentive to invest is going to be different.
Yes, but that's captured in my index, sufficient statistic index.
So I think that's what we're trying to figure out.
Okay.
You're making some kind of a sufficient statistic assumption. So basically what you're saying is, I'm going to assume that it's sufficient to just condition the capacity of the industry.
No,
The distribution.
no, this can someone, no.
You can write on the slide. The conference is over.
Okay, the conference is over. No, but I have to tell you how I do. Okay, so why don't so the trick is this pi of S here, like you have the pi of S, right? ST. My actual size that I use in order to train my basis functions is not constrained by my sample. It is because I've already estimated the parameters that goes into my payoff function. I've estimated the marginal cost production. I know the demand. This has no unknown parameters. So the period payoff in all the dynamic analysis had no unknown parameters. And so I can essentially generate this as a long vector at as many stage values as I can, as I want, as I, constrained to my capacity of my computer. I can have a million observations. All I need to do is plug in the S value and calculate what the profit should be. This provides a training sample for my basis functions. It's not limited to in fact, you do not want to limit. So this is a Bellman equation that I'm going to come back later. You actually do want, think about full solution method. I'm solving the value function at the entire state. Every possible value that, that characterize my state space. That's a full solution method. Indeed, you want to impose this restriction at, usually your data is already selected. There's the macro moments are highly correlated. You see the boom and bust, right? You don't really visit every part of the possible states. But in order to make sure the value function is satisfied everywhere, you actually want to expand this, including states that's not in your data. So I will come back to that later. Okay, so once I have essentially constructed my value function to be a function of
That expansion, for that to make sense, that's an interpolation, right? So you're thinking about like additional state points that are somehow
Yeah, exactly. I want my value function to be satisfied not just at my data point, but also outside my data point. That, to mimic the full solution method. The full solution method solves the value function for every data point, every value in the entire state space. I want to be able to, somehow mimic that. Okay.
We're just talking about a projection, right? Or am I
Yeah,
missing the
I
point?
think the confusion is about what variables would be in the projection. Maybe it's just me.
Yeah. Yeah.
I'll read the paper.
Yeah, okay. Because I still haven't finished telling you what to do next. So at least you can think about the value function is just a function of polynomials, okay? To fix ideas and unknown parameters. So now I can then, so this value function is a known function, just polynomials, to fix ideas, and then with some unknown parameters. But I can derive the marginal value. This is the marginal value of investment. This is marginal cost investment. So my I star has to make the marginal cost equal to marginal value. And then so essentially this equation tells me what's I star predicted by the model. And because nu, as a function of nu, because nu is random, it induces the likelihood of investment that I'm going to take to data. So effectively, as you can see, I have constructed, there's actually here as well, but ignore that. I've constructed the likelihood of investment, including positive and zero investment, through the previous equation here, right? Because I need to essentially choose investment I star to equalize the marginal cost and marginal benefit. And so the I star would depend on nu. That tells me that the likelihood function of I is just the likelihood function of nu times divided by the derivative. So now we know the likelihood function. So then the likelihood function, this part characterizes the likelihood. But importantly, I need to discipline the gamma because gamma enter into my calculation here. And the gamma, as you can see, this is how I discipline the gamma. It has to satisfy the Bellman equation. That's what I'm saying. Here, you don't want the gamma to just satisfy the Bellman equation within your sample, but rather you want to mimic the full solution method to expand this vector to include states that are not observed in a sample. That's very important, especially if your data is selected. Okay. So now you can estimate this, just like the standard MLE, and similarly the probability for entry, is similarly formulated. Okay. So practical considerations. First of all, as you can see, dimensional okay. So those are just for this question here. Sorry, wait. Practical. So the vector is high dimensional, and then so I use a few tricks. First, I assume the industry level price is a sufficient statistic for this market. I'm not, following each firm following of the capacity of the rivals. Okay. The second is I've used this. Some of the state variables, such as the region dummy, the ownership dummy, enters into my payout function linearly. They never change. So that's why I can use them as an index. So I collapse 10 of them into one, okay? And then I need to expand the state space, essentially to evaluate the Bellman equation. Yeah.
How high dimensional are we talking?
I have 7, actually, in a full specification, I think I have 8 continuous variables and 10 discrete state variables.
So the projection method makes total sense insofar that your data spans your space, because you want to be interpolating, right?
Yeah.
What you don't want to get into is that you're extrapolating. And so I'm trying to understand, if you have 7 different dimensions, to what extent have you spanned, has your data spanned that space?
This is the answer that I was discussing, that the choice of my basis functions is not limited to my data. I have 10,000 data points. That's actually not a limitation because I can span the state as much as I want because I observe,
You're only informed about the data within the
That's the likelihood, exactly.
of the span of those data.
Yes, but the likelihood function here, as you can see, the ultimate, the parameters, the degree of freedom, it depends on the gamma. And then the gamma here, I'm disciplining, sorry, the ultimate degree of number of parameters depends on the stuff that I put into. Maybe I have 10, actually for cost parameters, I just have a few. And then the gamma is disciplined by the Bellman equation. And this, I can have infinite number of observations if you like. And then so, okay, let me just skip off the results. I want to show you a few things that, from summary, what we have learned so far, right? So in this conference, we have learned a lot of things. So in a particular setting where you have a large number of state variables, the dimensionality reduction is very important. What are the things we have learned to reduce the dimensionality? You can use ergodic state that reduces dimensionality. You can use exchangeability. That's essentially a symmetry assumption. My rivals don't really matter as long as I control for their size. Oblivious equilibrium is another way to reduce dimensionality. Sufficient statistics. We have learned a lot about this in dynamic demand, where instead of tracking every product's attributes, I'm just tracking the sufficient statistics, the log sum, right? And in my case, I also have a few sufficient statistics, okay? And then, if the state variables enter into your payoff function linearly, that's actually easy. You can collapse them. The second one is I mentioned about constructing the value function. We have seen a lot of ways to do that. We have the full solution method. Okay, we can either do the value function iteration or the policy function iteration, or we can do the two-step estimation, where the key trick is you essentially write the value function as a function of the CCPs. We just learned it yesterday. Or you can do the forward simulation. That's BBL, right? You look at the policy in the data, and you just forward simulate. And that's how you construct the value function. The challenge in this setting here, as I argue, the policy function is biased. You can't, in a smart way, correct for the endogeneity in a selection of investment. And then the method I mentioned is value function approximation. And if you think about the core of the method, it's really how to come up with the basis functions. And I've argued the shape of the value function inherits the shape of the payoff function. Once you have estimated the payoff function, you can actually find you can expand your state space beyond your sample to train the basis functions. So I use a B-spline, but nowadays there's so many things you could do. You could do lasso, you could do ridge, you could do cubic splines, natural splines, smooth splines, you want to be fancy, or you could do neural network. Okay, I have a picture of a neural network. Here are your state variables. Here's your profit. You put in, this is one layer. You introduce a layer, the hidden layer, and then you can see that each layer will depends on all of the state variables. And this structure does a much better job in some applications at approximating, your payoff function. So I have here, first layer, those are the the neurons, and you have the out layer, essentially the first layer and then the output. This is often the G function is a sigmoid. We actually know a lot about this. We always use is 1 over 1 plus e to the power of negative nu. And then this F function, H function can either be linear identity or softmax, which is literally just a loaded function. So we use it a lot, in applications. And then you do a much better job. But then the question is, how do you know you have done a good enough job, right? Ultimately, you want to be able to discipline your parameters. And how do you do that? How do you do that? When do you stop? When do you think I've done a good enough job? Or maybe you need to graduate. There's a natural benchmark, because all we want to do is to solve the Bellman equation. The violation of, sorry, I keep hitting the wrong button. The violation of the Bellman equation tells you whether you have to do a good job or a crappy job. And that's essentially the ultimate bound. You essentially want to choose your basis functions together with the parameters, right? To minimize this as much as you can. And it's obvious whether you have done a good job or bad job. Unlike some other approximation methods where you don't really know. Okay, and then I won't tell you all the counterfactuals. You can do fancy stuff, temporary, targeting, long term, and this and that. Finally, I want to optimal design, etc. And I just want to see rationale. Okay, traditional rationale is spillover, some kind of externality. We don't find any strategic trade. Essentially, you grab the rents from other countries. We don't find that because market power is actually very limited. And there's externality. The spillover to other sectors, we also don't find that. There's no spillover to steel or labor market. And then we do find two. The first is trade. Indeed, according to our simulation, this has raised the trade volume by 140 billion a year. Very significant increase in trade volume. And this could provide justification and why UK and Europe and Japan were subsidizing shipbuilding. Indeed, international trade could be one justification. The second is what the editor wanted, the military considerations. We don't have good evidence for that, but we show you those two seem to be, military production and commercial production seem to be moving in the same direction. Okay, that's it. And then conclusions, it's not important. Thank you.